Welcome back to lecture 41. In segment 1, we derived a differential equation for T with respect to volume to be used for a plug flow reactor. Today we're gonna solve an example 8.4, in order for you to apply what you have just learned. I would like to bring to your attention that you may use the same coding that you have wrote, the polymath coding that you have wrote, for example 8.3 here, with some modifications. So please make use of your previous coding that you have wrote. طيب, example 8.4, liquid phase isomerization of n-Butane, continued. Assume that 70% conversions to be achieved in the adiabatic isomerization of n-Butane process discussed in example 8.3. Remember in example 8.3, the desired conversion was only 40%. So now assume that we need to achieve 70% conversion. Okay, so let's look at these profiles, the conversion and the temperature profile. So from the conversion profile, you can see that in order to achieve 70% conversion, you will need around 2.7 cubic meter reactor, and in order to, if you reach to around 2.7 cubic meter of the reactor, then the temperature will be somewhere around 260. Okay, so the temperature in this case will raise to 360 Kelvin at the reactor exit. At this temperature, a pressure of 1.5 megapascal is generated due to the vapor pressure buildup, which is greater than the rupture pressure of the glass vessel being used. So what do you suggest? We are still interested in achieving 70% conversion. However, there's a problem, which is the increase in temperature, which leads to buildup of pressure. So what do you suggest? I'm sure you're suggesting to lower the temperature inside the reactor. So to lower the pressure inside the reactor, temperature inside the reactor should be reduced. This can be done by using partially insulated tubular reactors instead of the insulated ones, right? So we had an insulated reactor, and so the reactor was operating adiabatically. The released heat from the reaction was staying within the reactor, therefore the temperature was increasing a lot. So what about using a partially insulated? This way, part of the released heat from the reaction can leave the system, and therefore we can maintain lower temperature. That's one solution. The other solution is to lower the feed temperature, because if you lower the feed temperature, you will certainly lower the temperature inside the reactor. Fortunately, there is a bank of 10 partially insulated tubular reactors, and some specifications are given here. For example, the U times A. Again, see the units here. It's per cubic meter rather than per square meter. So it's per volume instead of per area. And each is 3.5 cubic meter long. So we have these partially insulated tubular reactors. We have them in the storage shed available for use. We are also going to lower the feed temperature. Remember, the feed temperature was around 330, so we're going to lower it to 310 Kelvin. So we're going to do both tricks. The reactors are cooled by natural convection, where average ambient temperature in this tropical location is assumed to be 37 degrees C. The temperature in any of the reactors cannot rise above 325 Kelvin. So we have a few questions here. Does the temperature inside the reactor rise above 325 Kelvin inside these new reactors? Can we achieve 70% conversion despite the low operating temperature? So now we're operating at a lower temperature, which leads to a lower rate of reaction. So can we really still achieve the higher conversion, 70%, despite of that operation at low temperature? Last thing, explain the temperature and the rate of reaction profiles behavior. Okay, solution. So whatever steps we followed in example 8.3, we're gonna follow it here, except for the energy balance. That is because the reactor is no longer operated adiabatically. So which energy balance are we going to use? Remember, the reason that we needed to use the energy balance for was to get an equation for T, because T was a variable, so we needed an equation for T. So we used the energy balance. Can we use this equation? Well, this equation is valid, but it's difficult to solve for T because of the complexity we have here. So which one we're going to use? It's a single reaction, so we're going to use the equations written in terms of X. And we are designing plug flow reactor, so we're going to use this equation. Okay, very good. So we're going to use this equation, and we already know, well, we can simplify it. So we know that delta Cp is 0, so this goes to 0, and then we have dt by dV equals, I can write it as minus Ra because it's a positive value, minus delta H reaction because it's also a positive values, but it did not change anything in the equation, minus U times A times T, which is the temperature inside the reactor, minus TA, which is the ambient temperature, and it's constant, divided by FA naught times the summation of theta I CPI. We said we can call this guy, we can call it CP naught, right? And simply in this case, how many thetas do we have? Well, it depends on how many species we have in the feed. We have 2 species, so basically we have 2 thetas times CP naught, where CP naught equals CPA plus theta I, because we have 2 species in the feed, A and I, so therefore we have 2 thetas. Theta A is 1, and then we have theta I multiplied by CP I. Tamam? Okay, where this term is the localized heat generated, because we have an exothermic reaction, and this term is the localized heat removed, and this is the heat capacity of the reaction mixture. Okay, so we plug in the previous equation, actually replace the T algebraic equation with this T differential equation in the coding, in the polymath coding for example 8.3. So now we have a new coding, which is suitable for example 8.4, where the temperature is variable and the operation is not adiabatic. Okay, so let's look at the temperature profile inside the reactor. Okay, so we see that the temperature inside the reactor does not exceed 320 Kelvin. So it does not exceed our limit of 325 Kelvin, which is great. That's what was needed, right? And please note that we needed to look at the temperature profile throughout the reactor, not only at the exit, because this is not anymore an adiabatic reactor where the highest temperature would be at the exit. No, this is a reactor where we are exchanging heat. So at any place of any location of the reactor, the temperature could be at its highest value. Type question B. Can we achieve 70% conversion despite the low operating temperature? Well, then we plot the conversion profile. Okay, we plot the conversion profile, and indeed we can achieve 70% conversion. Tamam. Actually, we don't even need the complete reactor, which is 3.5 cubic meter long. We need only 1.8 cubic meter to achieve 70% conversion. But anyway, I have it 3.5 cubic meter, so that's fine. Absolutely fine. But remember, Shabab, here we are using 10 reactors, the whole bank of reactors available. So it's not anymore one reactor. So that's how I was able to achieve 70% conversion despite the lower temperature. Okay, the last part is to explain the temperature and the rate of reaction profiles behavior. So this is the temperature behavior, and we can compare it to the rate of reaction as well. We needed to explain the temperature behavior as well. So we need to explain the rate of reaction behavior and the temperature behavior. Okay, how can we do this? Well, in order to do this easily, we will also need to look at the energy balance equation, dt by dv. Because this is, when if I plot t versus v, if I plot t versus d, which is this plot, the slope would represent if the temperature is increasing or decreasing. So therefore, it's a comparison between this term and this term, which are the localized heat generated and the localized heat removed. Tamam? Okay, so let's plot these two quantities. Let's plot the localized heat generated and the localized heat removed. طيب. Let's begin with the temperature profile. So initially at the beginning of the reactor, we have high concentration of A, right, and low concentration of B. Remember, the reaction was A goes to B reversibly, and therefore the rate of reaction depends on both Ca and Cb. Higher Ca means higher rate of reaction, right? But higher Cb means lower rate of reaction. Okay, so at the beginning we say we have high concentration of A, therefore we have high rate of reaction. See, we have high rate of reaction in such a way that the localized heat of reaction, the localized heat of generation through the reaction is more than the localized heat removed. See, so the localized heat generated is more than the localized heat removed. Why is that? Because the temperature inside the reactor, which is around 310 Kelvin, is very close to the ambient temperature. So since the driving force is small for the heat transfer, the heat transfer rate is small as well. So the localized heat generated is more than the localized heat removed. The localized heat generated is high because the rate of reaction is high. The localized heat removed is small because the driving force, the difference between the temperature inside the reactor and the temperature outside the reactor is small. Tamam? Therefore, since the localized heat generated is more than the localized heat removed, since the heat released from the reaction is released at a rate that is faster than the rate at which heat is removed from the reactor, the temperature will continue increasing. Which will lead to the increase in the rate of reaction. As you can see, the rate of reaction here is increasing. However, after certain distance, the concentration of A drops, which leads to a drop in the rate of reaction despite the continuous increase in temperature. So obviously here, the effect of the decrease in Ca and increase in Cb on the rate of reaction is more than the effect of the increase in temperature. So the rate of reaction is decreasing. However, still the rate of reaction is appreciably high, leading to high localized heat generated. Tamam? And this localized heat generated is still more than the localized heat removed, despite the localized heat removed is also increasing because the temperature inside the reactor has increased. Tamam? So now the difference between the temperature inside the reactor and the temperature outside has increased, therefore the localized heat removed is increasing as well. But still the localized heat generated is more than the localized heat removed. That's why the temperature continued increasing. Tamam? Until I reach a point where the localized heat generated equals to the localized heat removed. See, we are at this point. Tamam? So we said the localized heat generated is decreasing because the rate of reaction is decreasing. Tamam? Due to the decrease in concentration of A and increase in concentration of B. Tamam? And we said the localized heat removed is increasing because of the increase in temperature inside the reactor, therefore the increase in the driving force for heat transfer. Type. So we are here now, they are equal. However, after this point, we see that the localized heat generated becomes less than the localized heat removed. Although both of them are reducing, but from this location onward, the localized heat generated is less than the localized heat removed. Therefore, the temperature continues decreasing. Tamam? Why the localized heat generated is small and decreased, and why is it smaller than localized heat removed and it is decreasing? Well, it's decreasing because the rate of reaction is decreasing. Why the rate of the reaction is decreasing? Because the concentration of A is decreasing as well as the temperature is decreasing. Tamam? Therefore, the localized heat generated is decreasing and it has a low value, lower than the localized heat removed. Tamam? Which is also decreasing due to the decrease in the temperature inside the reactor. However, its value is more than the localized heat generated. Why is that? Because we have substantial energy, so the substantial heat transfer drive, which is the delta T, temperature inside the reactor compared to the temperature outside the reactor. Okay, so now the temperature, as we said, continues decreasing because the localized heat is generated, or because the heat removed from the reactor is removed at a rate which is faster and greater than the rate at which heat is released from the reaction due to the low rate of reaction. Okay, I hope we explained the temperature and the rate of reaction profiles clearly. Right. Last thing to mention. Okay, so in example 8.4, tamam, this example, the one we just explained, we were operating at lower temperature compared to example 83, and therefore we had lower rate of reaction. Therefore, we needed to use 10 reactors in parallel, with each should be at least 1.8 cubic meter. Or instead of this, we can have one large reactor. So either we have 10 reactors in parallel where we divide the FA0 over 10 reactors, or we use one long reactor where it's fed by the original FA0. So you can see here that this is the profile in one long reactor, where the complete FA0 is fed to the beginning of the reactor. And in this case, in order to achieve 70% conversion, we need around 18 cubic meter reactor. Okay, please solve this at home and practice and analyze the reactor by changing different parameters to get to better understand this problem. Thank you very much, and we'll see you soon in another lecture.